Hello, everybody. Mr. Hennon here for the beginning notes on Chapter 5. I actually call this one Chapter 5 Plus. And the reason why I put the plus in there is because we're not only going to cover uniform circular motion, we're also going to pull a little bit of the universal gravitation law from Newton, which is actually from Chapter 4, and we're going to bring in the laws of planetary motion by Kepler, which isn't actually in Chapter 5, but I think it's very useful. So I'm going to try to get at all of those. But to start off with, we're just going to look at the dynamics of uniform circular motion. So what do we mean by uniform circular motion? Well, move that out of the way for a second. Move me over here. I think that's a little more out of the way. So the biggest thing with uniform circular motion is the object is moving at a constant speed in a circular path. So it's some kind of constant speed in a circular path. So if I watch this blue dot, it's moving at a nice constant speed around the center here. This would be the center of that red dot. Now the key idea also is we mentioned that it's the circular path and it's a constant speed. If I were to actually draw the direction of that speed at any moment in time, I always draw straight lines. And so these would be the direction of its motion. This would actually be its velocity. And so one of the things you will notice is its velocity is always in a straight line according to Newton's first law of motion. So I'm going to switch out my picture here, and let's imagine some kid is actually holding this airplane by some string, and they have this going around the circle, just like we did. This one's kind of it doesn't look like a circle, it looks like an ellipse, but it's because we're trying to kind of show a diagonal view. So this is showing the direction of the velocity and the fact that it's actually tangent to this circle. Now, testing your math knowledge, tangent means it's only going to cross this circle at one point, and that would be where this airplane is. The other thing that's very important, if you draw a radius, which would be right there, that the radius and the direction of your velocity are actually going to be perpendicular to each other everywhere you draw it. So if I draw the airplane over here, this is going to be perpendicular. If I draw the airplane down there, that's going to be perpendicular. So this is key that we have the direction of your velocity is actually tangent to the circle. It wants to go in a straight line. If we suddenly broke this rope broke, this airplane would just go flying off in a straight line this way. So this is why we refer to our circular motion this way. The next step is as we have something going around in a circle, there are different things that are going to be important. The radius is obviously going to be important, so we want to know the radius of that circle, the velocity of that object. Or since we don't actually care as much about the direction, we can just say the speed of the object and use v for either one. But the other one that's going to be important is t. This is the time it takes for the object to travel once around the circle. This is sometimes referred to as the period of its motion. So time period, if you will. And since it's going around the circle, if I just go back to the fact, this is from Chapter 2. Remember, I said each one of these things builds on itself. So our velocity was displacement over time. But in this case, we're actually going to be talking about distance over time. And so the distance is going to be the circumference of a circle. So we're going to have our 2 pi r here. This is just the circumference of a circle. And then t is the time it takes to go once around. So in uniform circular motion here, one of the key ideas is the speed is constant. Whoops, go back for a second. Sorry about that. Now, and that doesn't understand I want to write, the speed is staying constant, but the direction of your velocity is not. So if I look at a circle in A here, and at certain times, let's say at time 0, the object's right there, and at time P, or sometime later, it's there. If I take these two vectors, if I take this vector and I slip it up to here, I end up with this picture. And the reason why this picture is very important is because this little triangle that goes from C to O, and then if I drop straight down, which is the direction of this red vector, the P vector, and then draw this over, this should be a nice little right triangle. So theta plus alpha should equal 90 degrees, which I have written there. I also mentioned that the direction of your velocity is always tangent to the circle. So this is going to be tangent to the circle. So if I draw the radius here and that velocity, they would also be perpendicular. So alpha plus beta, these two angles equals 90 degrees. What this tells me then is beta is equal to theta. So this little angle right here is equivalent to this angle over here. And you go, why does that matter? So what I'm going to do is I'm going to do kind of similarities, and this really should be done with calculus. We're just going to try to do it without calculus. So when you go from one velocity vector to the tip of one velocity vector to the other velocity vector, this is the change in velocity. So if I take the change in velocity, which is from tip to tip, and then divide, and since it's moving at constant speed, if I just divide by the speed, I get this ratio right here. So this is coming from this picture. Well, that's just a triangle. Over here, this is the actual motion on the circle itself. So just kind of to go back, what they're showing here is they're showing this little picture here with the curve. Now, if I make that distance between O and P really small, then what you should find is, even though this is really a curved line, this is pretty close. If I make this small enough, this is almost equivalent to a straight line. So the smaller this gets, this curved line, the straight line kind of match. So these two triangles are similar. So the radius is similar to the velocity, and I put it on the bottom. And then the distance along here would actually be how fast it's moving multiplied by the time it takes to get from point O to P. And that's our delta T there. So I end up with this. So I'm setting the kind of a relationship between velocities, or speeds actually, and our time intervals and the radius. Now the reason I do that, if I take this delta t, and this v, and they switch places. In other words, I divide by delta t and multiply by v, I end up with this. And you go, well, why is that so important? Because this equation is important. The change in velocity over the change in time, that is the equivalent to acceleration. And what I'm showing is that it's equivalent to v squared over r. And I come up with a brand new acceleration. So rather than delta v over delta t, since I don't actually have a change in speed, that's really only going to help me. I actually have a change in direction. So remember, there were three ways to accelerate: speed up, slow down. Now we're dealing with that third way, that change in direction. So the direction of the centripetal acceleration, as we call it, is always going to be towards the center of the circle. So I tried to draw this little picture right here. If you imagine that picture is sitting right here, and I put this little velocity vector up there. So if I put this one and move it right there, what you'll find is that the direction of my change in velocity is going to be from here toward the center. It's always toward the center. That's the direction they're trying to show here, this toward the center direction. So that's why I put a little C on here. This is one of our equations, but this is what we call the centripetal acceleration. It's an acceleration toward the center of this circle. Now, going back to Newton's second law, we know that if you're going to have an acceleration, it has to be caused by a force. There has to be a net external force acting on that object. So acceleration down here is going to be equivalent to the net force acting divided by the mass. Or in other words, net force is equal to mass times acceleration. So when you have uniform circular motion, there has to be a net force to produce this centripetal acceleration. What do we call it? We call it a centripetal force, and it's always pointed toward the center of the circle. So something has to hold it into a circle. If you're spinning around in a circle, you have something spinning around in a circle, there has to be a force that holds it towards the center. And this is how we calculate that centripetal force. Really, what I did is I took F equals ma, that's just Newton's second law, but in place of this a, I put that v squared over r. So we've got another equation for finding it. But it's very important that we have this thing called a centripetal. And actually, the word centripetal means center seeking. Pedal is Latin for to seek or to search out. And so center is what we're trying to seek. So that's a little bit on the notes. We're going to go over some sample problems. I didn't put them into these notes, but make sure you answer the questions in the Google form, and we'll go for that tomorrow.